Cryptography Fundamental 7, Quadratic Residues Mod N. Remember at school that class where the teacher taught you how to square something? It was great, and where we loved to take the square of 3 to get 9 and the square of 5 to get 25. But in the next lesson we came back down to earth with a bump, as it was time to learn the nasty little square root operation. Now we had to find two numbers which, when multiplied together, gave us 121 or 196. Luckily, there was a convenient little button on the calculator that gave us our answer quickly. In the time before calculators, though, the working out of more complex square roots involved tables of logarithms. And so, in this podcast, I will outline the difficulty of a problem finding the square root in a modulo n world, otherwise known as quadratic residues. A hard problem. In cryptography, we look for a hard problem to solve. For this, we can create a backdoor into the problem and hopefully solve it. With discrete logarithms, we can use a hard problem of y is equal to g to the power of x mod p, and where it is difficult to determine x, even though we know y, g and p, but as long as we have a prime number which is large enough. Another hard problem that is used in the RSA encryption method involves the difficulty of factorizing a modulus which is made up of two prime numbers. But the problem we'll look in this blog post is around a hard problem of quadratic residues modulus n, and uses the form of x squared is equal to a mod p, and where we must find a value of x which results in a value of p, a mod p. If the solution exists, the value of a is a quadratic residue mod n. In modular arithmetic, this operation is equivalent to the square root of a number, and where x is the modular square root of a modulo p, of a modulo p. In the following, we will try and solve some values of x and also generate the Legendre symbol value. For example, if a is equal to 969 and p is equal to 1223, we get x squared is equal to 968 mod 1223. For this, we get a solution of 453 squared is equal to 968 mod 123. And if we have a equal to 1203 and p equal to 1223, we get x squared is equal to 1203 mod 1223. For this, we get a solution of 375 squared is equal to 969 mod 1223. The form of x squared equals a mod p is not always solvable. For example, if we have a equal to 209 and p equal to 1223, we get x squared is equal to 209 mod 123. This is not solvable. Also, if a shares a factor with p, it is not always solvable. It is also not solvable. For example, x squared is equal to 39 mod 13 will give a value of 0 as a return value for x. This is because 39 and 13 share at the same factor of 3. If we take a prime number of p is equal to 53, we get the following values that are possible for our solutions: 0, 1, 4, 6, 7, 9, 10, 11, 13, and so on. This means that if we have an a value of 0, 1, 4, 6, 7, 9, and so on, we can get a solution to x squared is equal to a mod p. I've given some examples in the related web post that you can try out. Legendre symbol. In science, it's difficult to avoid Adrien Marie Legendre, as there are so many things named after him: Fourier Legendre series, Gauss Legendre algorithm, and so on. But where does he help with our online security? Well, you will find his method used in elliptic curve methods, and which is used to protect our online identity and the security of communications that you have with this blog post. So let's look at the Legendre symbol. For this, we turn to Legendre, who in 1798 defined the Legendre symbol. In the following, we will try to solve the value of x and also generate the Legendre symbol value. Solve x squared is equal to 12 mod 13. With his method, we can determine that the answer is 8, as 64, that's 8 squared, mod 13 is 12. I've given some sample code inside the related web page. The quadratic residue thus involves solving y squared is equal to x squared mod m, and where we need to find the values of y for the different values of x for a given modulus m. For n equals 11, we get z underscore p star superscript star is equal to 1, 3, 4, 5, 9. This is because 1 squared mod 11 is equal to 1, 2 squared mod 11 is equal to 4, 3 squared mod 11 is equal to 9, and so on. To find the quadratic residues for a given modulus, we use the Jacobi symbol. This is a over p within brackets, and is defined as, if we get a value of 0, then a is equal to 0 mod p. If we get a value of 1, then a is not equal to mod 0, and we get some integer x, where a is equal to x squared mod p. And if we get a value of minus 1, then there is no such value for x. The Legrange symbol returns minus 1 when a is a quadratic residue of p, minus 1 when a is a quadratic non-residue of p, and 0 if a shares a factor with p. The Jacobi symbol was defined by Carl Gustav Jacob Jacobi as a generalized form of the Legrange symbol. Solving elliptic curve points. As we've seen in a previous podcast, we can have elliptic curve points which relate to y squared is equal to x cubed plus ax plus b mod p. For example, y squared is equal to x cubed plus 7 mod p. So is it possible for us to find the xy points which relate to this elliptic curve? So with this, we would substitute a value of x into our equation to get a value, and then we want to solve for y squared is equal to that value mod p. In this way, the symbols can actually show if we have a valid point to give us an xy point or not. In the related web post, I've added some examples of how we can use these symbols to be able to determine if we have a valid point or not on the elliptic curve.